Consider the iron roofing sheets used on many houses. After a few years of rain, they turn reddish-brown and start to decay. Yet a gold necklace can be worn for decades and stay perfectly shiny. This happens because metals have different personalities. Some are chemically aggressive and fight with the air and water around them, while others are stable and stay exactly as they are. Chemists rank metals based on this urge to change and interact. The more aggressive the metal, the higher its rank in what we call reactivity. This ranking system is the reactivity series, a ladder that organizes metals from the most aggressive at the top to the calmest at the bottom. At the very top are metals like potassium and sodium. They are so eager to react that they will fiercely attack almost anything they touch. Further down, in the middle of the ladder, are more reliable metals like zinc and iron. They still react with their environment, but they do so much more slowly. Down at the bottom are the calmest metals, like copper, silver, and gold. They are chemically independent and rarely interact with the elements at all. This ladder is more than a list. It allows us to predict exactly how a metal will survive when we put it to work in the real world. To confirm a metal's rank, we test how it behaves in dilute acid. When a top-tier metal like magnesium hits the acid, the reaction is aggressive. It instantly erupts into a cloud of hydrogen bubbles as it fights to change into a new form. A middle-tier metal like iron reacts with far less energy. You will only see a slow, steady stream of tiny bubbles. But if you test a bottom-tier metal like gold, it sits perfectly still. It refuses to react with the acid at all. The reason for these different behaviors is found in the structure of the metal's atoms, specifically the electrons spinning on the very outside edge. Highly reactive metals have an outer shell that is very unstable. This sodium atom, for instance, only has one other electron, and it sheds that electron almost instantly to find stability. The easier it is for an atom to throw away those outermost electrons, the more aggressive the metal becomes, and the higher it sits on the ladder. In nature, these metals are usually found trapped inside rocks. We refer to these metal-rich rocks as ores. Because top-tier metals are so eager to give away their electrons, they form incredibly tight chemical bonds with the elements in the rock. Breaking those bonds is difficult. It requires the intense, constant force of electricity to pull the metal free. Middle-tier metals aren't as deeply bonded to the rock. We can separate them much more easily by heating the ore with simple charcoal. The metals at the very bottom are so unreactive that they often refuse to bond with the rock at all. This is why you can find gold sitting perfectly pure in the earth. By looking at a metal's position on the ladder, engineers know exactly which method they must use to pull it out of the ground. Even after we extract a metal, we face a new problem. In their perfectly pure state, most metals are too soft and bendable to be used for building. This is because a pure metal is made of identical atoms, all the same size, stacked in neat, straight rows. When you apply pressure, these smooth rows slide right over one another. This is why pure iron or copper dents and bends so easily. To make the metal stronger, we melt it down and stir in atoms of a different size, known as an alloy. These new atoms wedge into the gaps, breaking the straight rows. Now, when you apply pressure, the layers jam and refuse to slide. We see this in the steel used to build a matatu. By mixing a little carbon into soft iron, we create a jagged atomic structure that can handle the weight and stress of the road. We even use this for our 500 and 1,000 shilling coins. They are made of brass, a mixture of copper and zinc, to ensure they stay hard and durable after years of being handled. By using the reactivity ladder to extract metals and mixing them into alloys to lock their atoms, we transform soft earth into the durable tools and vehicles we rely on every day.